In this video, we're going to go through the derivation of the integral test for series. So to set this up, we're going to consider a series, which really could start again from any k value, but let's just have the sum from k equals 1 to infinity of a sub k. Importantly, where we're going to assume that the a sub k terms are positive and decreasing. So a sub k plus 1 is smaller than a sub k. Given this, we're going to define a function. So it's going to be the continuous function such that f of k is going to be equal to a sub k for k equals 1, 2, 3, etc. Then, if our goal is to geometrically represent the sum of the a sub k's, we can represent this as a sum of areas of rectangles. Importantly, of width 1 and height a sub k. And recall that that's the same thing then as saying height f of k. We've started to consider, when we talked about Riemann sums, that this can be done in two ways. So let's consider each of these in turn. So first way I'm going to say is representing our sum as a left-hand sum on the interval from 1 to infinity. So again, I want to consider a graph of this f of x. We know that f of x is a positive function and it's continuous, and because f of x is defined so that f of k equals a sub k, we know that it is a decreasing function. So I want to draw an arbitrary function that has those properties. So let's start by sketching my axes. Maybe give myself a little bit more space. So let's assume my function looks something like this. So this is f of x. And I can now mark off my index values, 1, 2, 3, 4, and so on. And if I want to draw, let's draw this sum, and I'm going to draw it as a left-hand sum. I want to find the different terms of this sum. So remember the way that I'm defining this. The value of this function at 1, the y value, is the same thing as a1. And a2 is the value of this function at 2. And so I could mark all these values off on the y-axis here, but I want to think about these as now helping me to find the height of my rectangles that I want to draw. So I'm finding each height, which is the terms of my sum. And if I want to now sketch the terms of my sum as a left-hand sum, right, this is a1 plus a2 plus a3, etc., then I can find a1, and for a left-hand sum, this is going to be drawn in this way, and in this way, and so on. And I can continue this process indefinitely right? Because we want to have infinitely many terms. The next one would go here and so on. Importantly, these rectangles that I'm drawing, maybe I should use the highlighter. These rectangles here, each represent my series terms. So what I mean by that is notice that the width of the rectangles is 1 and the height is a sub k. So what you want to envision here is that if I were to add up the actual area of these rectangles, what I would get is the sum of my series. So the rectangle areas equal A1 times 1, A2 times 1, etc. So the sum of the rectangle areas is equal to my sum. So this is sum of rectangle areas. And finally, what I want to look at then is a comparison of those rectangle areas and the actual area under f of x. From my picture, we can see here that the sum from k equals 1 to infinity of a sub k, those rectangles appear to be larger than the actual area under the curve. And we know that's because we know f of x is decreasing. And importantly, those rectangles we can see have leftmost edge at 1, and then there are infinitely many of these. So when I'm comparing these, I have to situate my interval for f of x so that these match up. So the true area under the function f of x from 1 on to infinity has to be a lower bound for the value of this sum. Now, keep in mind what we're talking about here is that's not the only way to represent this summation. So I want to go back and look at a second way we could do this, and we'll see a different relationship here. So again, same function and really the same picture. So let's see, follow the way we wrote it. So the second way here is representing the sum from 1 to infinity of a sub k as a right-hand sum. And in particular, we're going to see that the interval here would be the interval from 0 to infinity. So again, we're going to start with the same general set of axes in our same general graph. So we want to sketch a function f of x that is positive, continuous, and decreasing. So something like this. And again, I'm trying to draw the same sum. So I want to sketch out the same index values on my graph here. So the same thing that we said before, the y value associated to each of these numbers that I've indicated on the x-axis matches up to the appropriate term in my summation from the way that we've defined f of x. So just like before, I want to find each of these desired terms of my series, but now I want to represent them in a different way. So let me use a different color. So now I'm going to use red to represent this sum as a right-hand sum. So notice that this is the exact same summation that we had before. So I'm still trying to draw a1 plus a2 plus a3, etc. Representing it as a right-hand sum, when I come and find this first term, before I would have drawn out from that red dot and moved to the right. That's what I did in the first method. But now I want this to be a right-hand sum, so I'm going to move leftward, and then I'm going to do that for each of these following terms. And again, this would continue as we move onward. So in this instance, same as before, let's consider the rectangles that we've drawn. And in particular, let's think of the resulting area of those rectangles. So we would have something like this. And again, this would go on indefinitely. A very important thing to think of here is this is a little different from when we looked at Riemann sums before. When we had Riemann sums, our goal was to take one integral and compare it to, say, a left and a right-hand sum over the same interval. So we had different sums. These two pictures I've drawn here, the rectangles are exactly the same. So those sums are the same. What is changing is the integral we're comparing it to, because we've kind of shifted the rectangles so that they lie on top of a different interval of x values. So when we represented that one sum as a left-hand sum, we compared it to the area from 1 to infinity, because that's the interval that the rectangle sat on. Here, when I do this, notice that the rectangles, when I'm treating this as a right-hand sum, in fact, actually sit on the interval from 0 to infinity. So I still have here, whoops, let me move back to the pen. I still have that my sum is a sum of rectangle areas that I've drawn, in this case in red. However, we get a different relationship. From the picture, I can see that this sum is now smaller than the integral of f of x if I integrate this from 0 to infinity. So I have two different bounds that I've constructed on this one sum from these two pictures. So I'm going to be able to put these together. So putting these together from these two different pictures, if I want to make a statement about the sum of these a sub k's, let's put that in the middle here. From our first picture, we saw that we had a lower bound for the sum, and that was the integral from 1 to infinity of the associated f of x. In the second picture, we found that an upper bound was the same integral, but over the interval from 0 to infinity. So this is going to be for our, specifically I will say the assumptions here though, where we had a sub k positive and decreasing, and we were assuming that the corresponding f of x that we construct is continuous. So as we go along, we'll see situations where we don't have these hypotheses satisfied. But given that we do, this is what we can use for what's called the integral test. So maybe let me, before stating this, I'll take a moment here to consider this box expression. So what can we conclude specifically about the series based off of what I've boxed above? So keep in mind our context is we're trying to determine if our series converges or diverges, and we're hoping that we have information about the integral of f of x that we can take advantage of. So to start with, this is going to seem similar to the comparison theorem for integrals, but I want to take advantage of whether or not knowing these integrals converge can affect the sum here. So for one thing, if we know that the integral from 1 to infinity of f of x diverges, note from the boxed inequality above that we're saying that that provides a lower bound, that diverging integral for our sum. So that automatically is going to mean that the sum from 1 to a sub k also diverges. The other direction, turns out it's just as nice, but it's a little bit harder to see directly, but I'll write it first, that if the integral from 1 to infinity of f of x converges, then the sum from 1 to infinity of a sub k likewise converges. So I need to explain that a little bit, because from the picture, of course, it is in fact knowing that the integral from 0 to infinity of f of x converges would give us that upper bound that would allow us to say the sum converges. I have intentionally put the bound of 1 here, and my goal in doing so is to be able to relate the bounds on the sum directly to the bounds on the integral and not have to think about that. But why is it that we can make that conclusion? I'll just have a little small note here. If you think about, if I told you that the integral from 1 to infinity of f of x, if I knew that that converged, let's go back up to our picture here. If I knew that there was finite area underneath the function from 1 to infinity, of course, I'm missing this first term under there, a sub 1, but that would tell me that the sum of the rest of the terms is finite because, again, we see the area under the curve from 1 to infinity. That's greater than the sum from 2 to infinity. So knowing that this integral from 1 to infinity converges implies that the sum from 2 to infinity converges. So how do I get from there to the statement that the sum from 1 to infinity converges? Well, that's because if I take the sum from 1 to infinity of a sub k, that's a1 plus a2 plus a3, etc., that's a1 plus the sum from 2 to infinity. So in this instance, we're already taking advantage of the fact that we know that the sum from 2 to infinity would converge. And that leaves this extra term a sub 1. But in all of our series, the terms themselves are finite. It's just the question of whether or not when we add all of them together, do we still get a finite number? So if I were to siphon off one term or even 10 terms or finitely many of them, that would not affect the convergence of the series. So knowing that the sum from 2 to infinity converges is enough to tell me that the sum from 1 to infinity converges as well. So putting this all together, we can actually state what the integral test tells us. So the integral test says that if f of x is, and we have several things that we're assuming, positive, decreasing, and continuous. And of course, when we're referring to f of x here, we're saying that it's the function defined so that f of k equals a sub k for k equals 1, 2, 3, and so on. As long as these conditions hold, then what we can conclude is that the sum of our a sub k's from 1 to infinity and the integral of f of x from 1 to infinity either both converge or both diverge. So importantly, keep in mind that in our context, we don't know about the series. The hope is that we can construct this integral, an improper integral, determine whether or not that integral converges or diverges, and then use the integral test to make the same conclusion about the series. Just a quick note, the key thing and the reason that I went through this note above is that generally with my statement of the integral test, what we're kind of pointing out here is that you can always choose the bounds on the integral then to be the same as those of the summation. And that's true regardless of whether the integral converges or diverges. So if you encounter a sum that starts at, say, 10 and goes to infinity, likewise you can then integrate from 10 to infinity. So kind of matching those up in the same way that they're presented on the summation. So in the next video, I actually want to go back and use the integral test on some examples. But among all of the tests that we're going to look at, this one is probably the most involved in terms of seeing why it's true and why these hypotheses are important. But we really do want to understand where this comes from because that's going to help us in using the applications. And further, when we talk about error bounds, we're going to come back to this idea of the picture associated to the integral test.